So today we're going to talk about OOP class relationships, and there are two kinds of class relationships. The first one is a type-based relationship, and the second one is dependency-based relationships. Type-based relationships are characterized by how two classes are related to each other through ontological hierarchy. For example, a mammal class's relationship with an animal class's relationship is an example of a type-based relationship. That's because if you imagine a mammal, for example, as a type, a mammal is considered as an animal. But the reverse is not true. An animal is not necessarily a mammal. There are two types of type-based relationships, or there are two type-based relationships. And actually, there can be an extra one as well, which is sort of a hybrid of these two type-based relationships. But the important ones are these two, realization and specialization relationships. So we have already seen some examples of this when we've introduced the paradigm and when we've introduced the fundamental concepts of object-oriented programming. The first one right here is a realization relationship. A realization relationship is a one-way relationship that describes how something is realized by something that is concrete. Something abstract is realized, meaning it is given a real form or given concrete form. Given a realization class and an abstraction class, you say a realization realizes an abstraction. So if this class right here is your realization and this class right here is your abstraction, then you say that R realizes this abstraction. There are other names for realization. A realization relationship is also called an implementation relationship. And in an implementation relationship, we also call a realization the implementation and the abstraction the interface. An implementation, you also call this relationship. An implementation, of course, implements, that's the verb that describes this relationship. An implementation implements the interface. Interface is also a fitting term for abstractions because it is through these classes that other objects interact with each other. And the term abstraction that I'm using here is in this specific context is the construct abstraction, which is a type of a class or a special relationship, uh, a type of class in a relationship. So an abstraction in terms of an interface, because again, I've already told you about this in the previous lectures where the term abstraction is quite overloaded. It could mean the concept abstraction, but in this case, we're talking about abstraction as the construct, the type of class. An abstraction as like contrary to a realization. An abstraction is a special type of class that does not contain any implementation. This means that abstraction doesn't have code that controls the form and behavior of the class. We will discuss actual examples of abstraction and realization, as well as specialization relationships in code, which will be written in Python for this specific course. But for now, we're going to talk about this as a concept, which is regardless of whatever programming language you use. So, again, it is a special type of class that does not contain any implementation. What this means is that abstraction does not contain any code that controls the form and behavior of the class, meaning it does not contain any attributes, it does not contain any specific behavior. It does contain methods, but these methods are empty. It only contains code that specifies how this class interacts with other objects. And this is actually where the term interface makes sense. because an abstraction interacts with other classes through this interface lang. So these abstraction classes, they appear useless at first because it doesn't actually do anything. I mean, what can you do with something that does not contain form or actual behavior? It's just an interface. It's just a face. It's just a facade, for example. So they appear useless at first since it doesn't do anything at all. In fact, you cannot even create an instance of an abstraction. It's not allowed at all. And even if you do, it will be pointless since it doesn't have code that controls how it behaves. I mean, what is the point of creating something that is abstract when it cannot uh, materialize in the real world, for example? At the end of the day, an abstraction is a representation of something that is abstract as well. So, an abstraction can only be useful if some other class realizes this abstraction, and this is where the realization relationship is established. These realization classes provide abstractions their form and behavior. So, an abstraction, yeah, can only be useful when some other class realize it through this relationship called realization. And this realization class is just your normal concrete class that contains form and behavior. And this is where an abstraction truly becomes an interface of something because another class, for example, I'm going to call it C, interacts with with any class or this realization, for example, through this interface of an abstraction. And I've given you an example of this when we talked about the paradigm itself, when we talked about the concept of data hiding, and when we talked about the difference between the surface and the volume of what these classes represent. You might ask the question though, what's the point in maintaining some realization relationship between classes? If abstractions can only be used through their realizations, then why create the abstractions at all? It seems like the creation of these abstraction classes are pointless because they don't actually perform anything, they don't actually represent anything concrete. They're just means, they're just middlemen, or they're just interfaces for other classes as well. So, what is the point in writing them? It seems like you're just writing extra code. It seems like you're just uh, creating extra layers of separation between two classes. So the importance of this seemingly pointless relationship lies in OOP's data hiding principle. And we've talked about this as a paradigm, and we will actually explore more about why these relationships are very common in a future discussion about solid principles. But for now, I'll show you one of the reasons why this is useful through an example. So this is one of my favorite examples to use, the concept of a borrowable item, which is something that does not have a concrete representation in the real world. So, or it is something that is a representation of something in the real world that does not have a concrete form. It is a borrowable item. It is something that can be borrowed. So, for this specific example right here, you have a library system. And in a library, you are able to borrow resources such as books, newspapers. Sometimes I call them periodicals to generalize them. And then IMAX, for example, computers. When the library system interacts with these resources to facilitate transactions such as borrowing and returning, for example, and if you remember the class that I used to interact with these borrowable items is the library card, which interacts with borrowable items by borrowing them. And when they borrow them, they basically sort of append this specific borrowable item to a library card thing, right? That's what happens when you borrow a book. Your library card becomes updated saying na, ooh, these are the resources of the library that you have borrowed so far. So, when the library system interacts with these resources to facilitate these interactions, borrowing and returning, for example, the library system treats these resources right here as your regular old borrowable item. It doesn't really need to concern itself of the specific type. Operating like this is actually better for the library system for reasons such as maintainability and future proofing. We will again explain more about these maintainability and future proofing reasons when we discuss in detail about solid design principles. So therefore, the best architecture to use in this situation is to make each resource type, books, newspapers or periodicals, and then computers, for example, you make them realizations of some abstract borrowable item. So a borrowable item class would merely be an abstraction. This class, again, since an abstraction does not contain any behavior or form, so the borrowable item would contain no attributes and no method bodies. And it does make sense. I mean, how exactly do you represent a general borrowable item? Like, how does it behave or how does it look like? It's merely abstract. What we know though is that any borrowable item can be borrowed. These are the sort of uh, the requirements for borrowable items. They can be borrowed and they can be returned. So what we know is that these borrowable items can be interacted with through these transactions right here, borrowing and returning. So you imagine this borrowable item right here would contain skeletons for the methods borrow and return. I say skeletons because, again, these methods do not contain any implementation at all. They only contain specifications on how you invoke these functions, meaning uh, it would contain the return type of these methods, it would contain the attributes and the parameters of these methods, and what are the types of the parameters of these methods. So it doesn't have any specific behavior. It only specifies how it interacts with others. For example, a library card, how does it interact with a borrowable item? It calls the function, let's say, borrowable item b dot borrow. So that is one interaction for library card. It could also interact with it through b dot return, for example. So there's actually a special name for these methods right here, methods that do not contain any body. It doesn't contain specific behavior at all. They're just names and types. You call them abstract methods as well. And any realization of borrowable items such as these books, newspapers, and IMAX, for example, since you've established this realization relationship between them, so any realization will be forced to implement the borrow and return methods as well. So any realization will be forced to do that, meaning it needs to include these methods with each of their own method bodies for borrowing and returning. So by establishing this realization relationship between these three to this borrowable item abstraction, then you will be basically saying that you are forced to implement the transactional methods borrow, return. It should contain borrow, return, borrow, return. And this time, these borrow and return functions must contain implementations now. And this is where behavior for borrow and return will be placed. So you will not be writing skeletons for borrow and return, you'll be writing full borrow and return functions inside these realizations right here. So it will need to include these methods with each of their own method bodies for borrowing and returning. And this is the beauty of making borrow and return abstract, because it is very possible for different realizations to have different implementations for borrow and return. So how do you borrow a book, for example? Is there a difference between borrowing a book transaction and borrowing a newspaper transaction? Like, are there different due dates? Are there different penalties if you're returning them late? So these differences in implementations will be characterized by the differences in the bodies of borrow and return inside different realizations as well. And all of those differences will not even be revealed to the library card, because the library card is treating them just like any normal borrowable item. And this is how realization relationships actually enable one of OOP's most important uh, most important design concepts, the concept of polymorphism. So since a book is a borrowable item, oops, I think I skipped showing these things right here. Since a book is a borrowable item, allowing the library system to interact with it like any other borrowable item. So the library card right here, one of the library system's classes that transacts with borrowable items, it treats any instance of borrowable item just like any other borrowable item lang. But at the same time, a book is also a book as well. Therefore, it behaves in the same manner a book behaves. It is borrowed in the same manner a book is borrowed. It is returned in the same manner a book is returned. It just so happens that a library card is treating it just like any other borrowable item. And this is an example of polymorphism, because in this specific context right here, a specific instance of book is treated as one form, which is library card, but it behaves as another form, which is specifically a book. So by building all of these relationships, the library system is able to interact with resources without explicitly knowing which exact resource it is. The system knows that it is borrowing some instance of borrowable item, but it does not know if it is a book or a newspaper. The exact type of this instance will then behave depending on its type. Although all this effort may seem unnecessary for now, you will learn in this course that through the establishment of many of these relationships, OOP is able to uphold one of its core design principles, which is data hiding. And just to sort of allude to one of the reasons why these relationships are very common in object-oriented programming design, these kinds of relationships make your system very maintainable. So for example, if ever you change your library system and there's a new type of resource that can also be borrowed, all you have to do is simply to create that new type of resource, establish a realization relationship with borrowable item, forcing it to implement borrow and return. Therefore, this will automatically make your new borrowable item realization a borrowable item as well, because it will be forced to contain borrow and return. We will have concrete examples of this written in code when we talk about Python OOP syntax, so realization as well as specialization, which we will discuss right now. So specialization relationships are actually very similar to realization relationships. And you can think of these specialization relationships as realizations, but between two real or concrete classes. So if a realization relationship is between an abstraction and a realization, meaning something that is abstract and something that is concrete, a specialization relationship is a relationship that is between two concrete classes. A specialized class is specialized by some general class. By establishing this relationship, you are able to extend the form and behavior of a specific class. And these are other names for this relationship right here. Specialization sometimes is called an extension, or sometimes called, I forgot to write it here, inheritance relationship. And here are other names for the players in this relationship. So if you have a specialization which specializes some generalization, for example, you also call the specialization a child class. If this is the child class, then the generalization is your parent class. So specialization can also be called a subclass, and if this is the subclass, then the generalization is called the superclass. So the verb that describes the relationship, you could call them specializes. You could also call them extends. You can also call them inherits. So child inherits, parent, sub extends, super, and etc. Okay, so an example. So here's an example that would illustrate what the specialization relationship means. So if you consider a factory, for example, that builds robots, this factory is able to build these normal bots right here, which are general type of robots. Instead of creating entirely separate mechanisms to build each type of robots, because there are other types of robots as well, skybots, shadebots, and shadowbots, for example. So instead of creating entirely separate mechanisms for those, the factory is able to exploit the fact that the other robots are just specializations of normal bot. For example, Skybot is just the same as normal bot. It just so happens that it has an extra flight capabilities because of these wings right here. Shadebot is just the same as a normal bot right here, but at the same time, it is special because it contains extra UV protection, for example. So, the way the factory is able to exploit the relationships between these classes right here to normal bot. So all they need to do is to add extra layers of construction, such as adding wings or outfitting shades. So if ever you're constructing a skybot, you're not gonna sort of create a mechanism for creating skybots from scratch. You just have to create normal bots, build a normal bot, for example, and then add extra construction add extra layers of construction, such as adding wings, for example, thus automatically converting this normal bot into your regular old skybot. So specialization relationships work like this as well. When you write code for the general class, you do not need to rewrite that code for its specializations. What you write inside specializations are the attributes and methods that make it special. So for example, what are the things that any general robot must have? It must have its body parts, for example. It has a head, it has arms, it has a torso, for example, and it has legs. But since you want to create a specific skybot, you don't have to write code for head, arms, torso, and legs, for example, because that will already be implemented in your general class. What you need to write inside Skybot are just the special things that make Skybot Skybot, and that would be the wings, for example. So if this specialization has flight capabilities, then you add attributes for wings. If this other specialization, for example, has UV protection capabilities, so you add attributes or methods for shades, for example. This specialization, Shadowbot, a specialization of Shadebot, has a knife, for example. So you just add what makes ShadowBot special from ShadeBot. So if any specialization behave in a different manner for some specific method, then you can also change the specific method as well. For example, if you want a specialization, if you want ShadeBot specialization to have a spike on its head, for example, then all you have to do is to re-implement what head does. And the head part right here will be changed from ShadeBot's head, or sorry, from NormalBot's head to ShadeBot's special head. So because of these relationships right here, you only need to write one copy of the code that is common for the general class and its specializations. So whatever is general for all of these things, whatever is common, whatever is default for all of these robots must be written in the NormalBot class. So this means that you do not need to rewrite said code, saving time and effort, but more importantly, having one copy of code helps us for maintainability. Why is that? So when the recipe for all robot types need to change, for example, let's say you have found a better way of building heads, for example. So uh, just by changing the head right here, sorry, let me rewrite the attributes right here since my penmanship is not good enough. Head, arms, torso, legs, for example. So for example, you found a new way of creating head, for example, in a better way, then you just change the head implementation that was found inside the general class NormalBot. So you now have head plus. And automatically, all of your specializations would have implementation for head plus as well, except for those implementations that contain head plus as well as overrides for head. For example, if your shadebot was indeed implemented with different kinds of heads, since it has its own special way of creating a head, it will not automatically have the implementation for head plus. It will still use its own head implementation. So we will have examples of this specific there's code written for this specific example. Actually, we will discuss that when we talk about Python OOP syntax. So when the code for general class and the special classes need to be updated, all you have to do is to change the shared code found inside general class. Changing that will automatically affect the special classes as well. Through this mechanism, specialization relationships enable inheritance, one of OOP's core design principle. And this is where the term inheritance and extension makes sense, because special classes inherit all of the attributes and methods of the general class in the same way that a child inherits something from its parent. So Skybot inherits heads, arms, torsos, and legs from NormalBot. So the term extension also makes sense because Skybot extends the capabilities of NormalBot because of the added attribute wings, for example. And another note, you can also specialize specializations as well. You can see this as an example with ShadowBot. ShadowBot is the specialization of the specialization ShadeBot. So for this specific relationship that you see right here, ShadowBot is a specialization of ShadeBot, which is a specialization of NormalBot as well. And through this relationship right here, this will automatically mean that ShadowBot is also a specialization of NormalBot, but implicitly lang. That is because everything that is inherited by NormalBot will be inherited by ShadeBot. And since these things appear in ShadeBot implicitly as well, then that would be automatically inherited by ShadowBot as well. So since ShadowBot is a special ShadeBot and ShadeBot is a special NormalBot, ShadowBot is automatically a specialization of NormalBot as well. Specializations also allow polymorphism in the same way realizations do. A shadow bot, oh, there it is. A shadow bot can be interacted with like any normal bot or shade bot, but since it is also a shadow bot, it will behave specifically like a shadow bot. So, for example, if you want to uh, try to interact with normal bot in the same way, try to interact with an instance of a shadow bot, for example, a shadow bot can be interacted with as a normal bot, but it will behave as a shadow bot because it is specifically a shadow bot. It is both a normal bot and a shadow bot. Again, having multiple forms, enabling polymorphism. Moving on to the third sort of type-based relationship. This is the abstract class. And an abstract class is something in between an abstraction and a generalization. It contains attributes and methods with bodies, but it also contains abstract methods as well. If you remember, an abstraction, it does not contain attributes. It contains methods, but these methods are abstract, meaning these methods are just skeletons. These are abstractions. You have normal classes, the default classes. It can contain attributes, and it can contain normal methods, meaning methods with bodies. And abstract classes are something in between abstractions and concrete classes. So abstract classes can contain attributes, can contain methods, full methods with bodies, but it can also contain abstract methods as well. So when classes specialize/realize abstract classes, they inherit the attributes and methods with bodies, but they are also forced to implement the abstract methods as well. So if you have another class, for example, called D, for example, and if they inherit/realize, since they do the same thing, they do both at the same time, this D class right here will inherit all of the attributes. This one and this one will be inherited, but it will be forced to implement methods, meaning it will be forced to rewrite the methods with names na. You will see an example of this when we discuss Python syntax. So these relationships are sometimes used if the system requires a mix of inheritance and implementation between classes. So if the relationship that you really need for these two classes is something in between a specialization and realization, you use abstract classes. The next type of class-based relationships, and these relationships are sort of more like object-based relationships actually. But the best way to call them are dependency relationships. Dependency relationships are also known as associations, which characterize how two classes interact with each other. So a class which is dependent on another class needs to know how to interact with it. These interactions range from being used as method parameters, being returned in methods, being used inside method bodies, being used as attributes, and etc. And if you remember the example we had a while ago, I have to go back so far. So an example of this dependency relationship that I've already discussed is this library card right here. Since library cards borrow borrowable items, library card is dependent on borrowable item. This is a dependency. So a dependency relationship is one way, but it is also possible for two objects to be dependent on each other. And if you have a class right here, which is dependent on this class, so for example, the library card and a borrowable item, for example, these two classes. So we call the library card the client. and we call the barbell item the dependency. So the verb that describes this relationship is dependent. So the client is dependent on the dependency. Sometimes we call again this relationship the association. The client is associated to the dependency. So a dependency relationship is just a broad relationship that may actually mean one of two things. There are two types of dependency relationships: aggregation and composition. So let's talk about the first one, aggregation relationships. Aggregation relationships are general usage and transactional dependencies. When a dependency is an aggregate of some client, it means that the client merely uses the instances of this dependency. And this is the keyword here, usage. It uses the instances of this dependency. These relationships are looser forms of dependency because the dependency instance can exist outside the lifetime of the client instance. So an example of this relationship right here, in a video game, a hostile enemy instance, for example, a dragon priest, when it spawns in the video game, it is equipped with instances of dragon priest mask and dragon priest staff. These instances right here. So these are different classes by themselves, and it just so happens that a dragon priest uses these classes as well, since it is equipped with them. Dragon priest mask or dragon priest interacts with these dependencies to calculate its attack damage and its defenses, for example. So when it attacks, since it depends on the exact type of dragon priest staff, for example, then its damage is calculated based on or dependent on this class dragon priest staff. When this enemy is attacked, for example, it will be dependent on the dragon priest mask to calculate its defenses, because the dragon priest mask sort of serves as one of the armors of one of the pieces of armor for dragon priest, for example. So when this specific instance of dragon priest is defeated, it despawns, but it leaves behind the dragon priest mask and dragon priest staff. So when it dies, it despawns. It is ceased to exist from that state of the game, for example. But it leaves behind these two dependencies right here, dragon priest mask and dragon priest staff. These instances will continue to exist since it can still be used by other client objects in the game, such as the player character. For example, the player character can pick up these weapons and these armor pieces, and it can store it to some storage chest, meaning it will now exist in some storage chest, for example, if you put it there. And what this means is that Dragon Priest, the relationship between the Dragon Priest right here with Dragon Priest Mask and Dragon Priest Staff is merely aggregation, because the Dragon Priest merely uses these equipments, these classes. On the other hand, the second type of dependency relationships is the composition relationship. So composition relationships are ownership dependencies. When a client is composed of some dependency, this means that the client owns the instance of the dependency. So that is your keyword there. It is, instead of usage, it is now ownership. These relationships are stronger forms of dependencies since the existence of the dependency instance is tied to the client, meaning the dependency ceases to exist outside the lifetime of the client instance. So in the same video game, for example, when a dragon priest spawns, when it appears in game, it appears using some dragon priest character model. I forgot to write it down right here. Dragon priest character model. So it appears using the Dragon Priest character model. It's three-dimensional representation in the video game's context. So when the Dragon Priest instance is defeated, it despawns, and it would make no sense for this class right here, the Dragon Priest character model. It doesn't make sense for that instance to stay behind after the Dragon Priest instance is defeated, because it wouldn't make sense to show the character model if the Dragon Priest doesn't exist anymore. So it makes no sense for that instance to stay behind after the Dragon Priest instance is defeated, therefore it ceases to exist as well. So this must also despawn. This means that the relationship between Dragon Priest and the dependency Dragon Priest character model is composition. So this is sort of the rule of thumb to use when you want to specify exactly what kind of dependency is or is between, what kind of dependency relationship is between these two classes. Is it specifically composition or is it specifically aggregation? The way you sort of see that is to check if these instances exist outside, or these dependencies exist outside the lifetime of the Dragon Priest instance or the client classes. And that is all. Again, we are gonna discuss how you write these relationships in code, specifically realizations and specializations. And that is all for this one. Thanks.